In an earlier video, I promised to come back to that data later, and it was the one about the comparison between homework grades and test grades in a Math 118 online class I taught in winter of 2011. So in that example, we're looking at the relationship, if any, between homework and test scores. And so I worked that out, and the handout, you should have the handout either by email or on the website. Anyway, there was a second page of that handout where I've revisited that same data, homework and test scores for this class. And I used this approach to studying it. And so here it is. You should have this somewhere. And it has all the regression sum of squares, total sum of squares, residual sum of squares, all calculated out. As you can see, it's kind of a pain to do all that stuff. And no one in their right mind would normally do this without having some software. And but anyway, I worked it all out, and I'm going to go to the summary table. And here this time the source are the test scores. So we're measuring test scores versus homework scores. And now, did I get that right? Test scores. No, it should be homework. Sorry about that. I see that on my handout I have. Maybe I'll fix it before you see it. My source should be actually homework. Okay, so if that's not fixed on your handout, please fix it. Alright, we'll try that again. So the source are the homework grades, and which is the independent variable, and based upon homework, what can you expect as a test grade? That's the idea of this analysis. So the sum of squares added up to 1,558 for the homework. For the regression sum of squares, the residual sum of squares were 2,658, and the total is 4,216. So just a little disclaimer here. All these numbers on here are integers. However, they've been rounded off. There are decimals involved that are hidden because they've been rounded off. So if you were to actually take my numbers and do the same calculations, you might be a little bit off due to rounding errors. Okay, so the proportion, if we take the regression sum of squares and divide by the total sum of squares, we'll get this proportion, which is 0.37. And that, as we said before, is r squared. So apparently 37% of the data is explained by the relationship between homework and test scores. The other 63% is due to residual variables, residual effects. And that matched the number we got on the earlier analysis in the earlier video. R squared was 0.37. So the correlation coefficient, if you take that square root, you get apparently 0.61 is the square root. So it's a moderate correlation, and from there. Okay, well, and the other proportion is the complement of 37, so it'd be 63. So 63% of the data is explained by residual effects, and of course this adds up to 100%, or 1. In this chapter, regression analysis, that always gets 1 degree of freedom, because we have one variable x. One variable x, 1 degree of freedom. And there were 25 pairs of data. So with 25 pairs of data, n equals to 25, then the total degrees of freedom will be 1 less than that, will be 24. So 1 less from n is always this number, and then this number here, residual degrees of freedom, is always the difference between the two. So that would be 23. Well, the mean square will be sum of squares divided by degrees of freedom. So the first one's always easy. 1558 divided by 1. And then the second one will be this number, 2658 divided by 23. And that came out to be 116. Now on my page I've got these to 2 decimal places. And so 1558.29 and 115.56 is what I have on my page. The F ratio is the division of this number divided by that number. It's the ratio of the regression mean square divided by the residual mean square. So if I divide those two numbers, I get apparently 13.48. So, and again, I don't know if you'll get exactly 48 here if you divide these integers. It might be a little bit off due to rounding effects. All right, so let's see if we can find that in the book. And this time we're working with 23 degrees of freedom in the denominator. And the book does go to 23. It's on page 660. 660, 23 degrees of freedom is up here near the top. Oops, I'm sorry. It should be 24. Correct that, please. It's 24. No, it is 23. All right, sorry about the hesitation there. This is the denominator degrees of freedom is 23, so we will be using 23. Denominator degrees of freedom is 23. Numerator degrees of freedom is 1, so it's the first column. And if you look there, 13.48 actually fits between two numbers on this chart, because the numbers go 2.94, 4.28, 575, 788, and then 1420. And so our number, which is 13.48, slips in between here, and which means the p-values between these two p-values, and those two p-values are 1% and 1/100th of a tenth of a percent, so it's 0.010 and 0.001. So it's very small. We're going to reject the null hypothesis. In other words, we have a significant correlation here, and I would say it's less than 0.01. So p is less than 0.010. So there we go. Now that's the best we could do with that chart. I used the Microsoft Excel, a spreadsheet, and it calculated the p-value, and actually my more exact p-value is 0.0013. All right, so now I think have an interesting quandary here, because the software contradicts the table. Software contradicts the table, and I think I just realized, I'm thinking on my feet here, what's happened. Because if you look at, you have my first page handy of this handout. We calculated the p-value. I calculated it from, again, Microsoft Excel, and the p-value, when I did the first regression analysis on this, the p-value was not this number. It was 0.0006. I was wondering how to explain that, and now I know. Okay, because the software I have, I read up on the software I have. I looked up in Wikipedia the F ratio, because I wonder how come I'm not getting the same numbers here? Shouldn't I get the same numbers? And the true F ratio, I'm sorry this is going to be, hope this isn't too confusing. If you don't get it, don't worry about this part. But let me try it, explain why I have a difference here. When I looked up the F ratio is a two-sided test, not a one-sided test. So the hypothesis testing we normally do is one-sided. We look at only one side of the bell curve, the normal distribution. The F ratio gives us both sides. What's the probability of being either here or over there? As you can see, it'd be double. It'd be about twice this number, roughly. And so that's what my software gave me. I suspect our author has altered this table to be one-sided, because according to my table it should be less than this number, and according to other analysis that's really what it should be. So these are consistent. So like I said, if you didn't get that little explanation, don't worry about it, it's a throwaway. But I wanted to explain to you the discrepancy in numbers here, and now it just hit me why I think our author's F-ratio table fits this kind of analysis and is one-tailed, not two-tailed. Whereas traditional F-ratio analysis is two-tailed. So anyway, it doesn't matter in the long run with this problem because in any of these cases, the p-value is very small. We reject the null hypothesis. We have a statistically significant correlation. In this case, a positive correlation. So there you go. That's your introduction to these sum of square tables.